Welcome to Mathematical Physics. Today, we are going to explore a fascinating topic that explains how physical systems respond to outside forces. We will be learning about complementary and particular integrals. If you have ever wondered how a car's suspension absorbs a bump, or how a bridge sways in the wind, you are in the right place. We will build this concept from the ground up, starting with a simple, intuitive analogy, and then moving into the rigorous mathematics. By the end of this video, you will understand exactly how to split complex differential equations into manageable parts. Let us dive right in. To understand the math, let us first imagine you are riding a bicycle over a continuously bumpy cobblestone road. The bicycle has its own natural bounce because of its suspension springs. This natural bounce happens even if you just push down on the seat once and let go. However, as you ride over the cobblestones, the bumps in the road force the bicycle to bounce in a specific, continuous rhythm that matches the surface of the road. The total bouncing motion you feel is actually a combination of two different things: the bicycle's own natural bounce and the forced bounce caused by the road. In physics, we separate these two behaviors to understand the whole system. Now that we have our bicycle analogy, let us look at how this translates into formal mathematics. In the study of differential equations, a system acted upon by an external driving force is represented by a non-homogeneous equation. To solve it, we split the solution into two distinct parts. First is the complementary integral. We find this by temporarily pretending the external force is zero. It contains arbitrary constants and describes the system's natural, unforced dynamics, just like the bicycle's natural bounce. Second is the particular integral. This is a specific solution that accounts entirely for the external force, containing no arbitrary constants. Together, they give us the complete picture. You might wonder why we go through the trouble of splitting a single problem into two separate mathematical pieces. In real life, systems are constantly subjected to external forces, like an electrical circuit connected to an alternating current, or a bridge vibrating under heavy wind. The complementary integral tells us how the system behaves initially, before settling down. We call this the transient response, and it usually dies out over time due to friction. The particular integral tells us the steady-state response, which is how the system behaves long-term under the continuous influence of the external force. Without this separation, designing safe bridges or stable circuits would be incredibly difficult. This brings us to the mathematical representation of our physical system. What you see here is the standard form of a second-order linear non-homogeneous differential equation. It acts as the blueprint for our system. The variable y represents the state of our system, such as position, while x represents time or distance. The coefficients a, b, and c are constants representing physical properties like mass, friction, and spring stiffness. The crucial part is the term f of x on the right side. This is the external driving force. If this force increases, the system is pushed harder, directly changing the particular integral. If we set it to zero, we isolate the system to find the complementary integral. Once we understand the blueprint equation, we can write down the structure of its final, complete solution. The function y of x represents the total, complete behavior of the system at any given moment. It is simply the sum of our two mathematical pieces. The term y sub c is the complementary function, representing the natural, unforced behavior. The term y sub p is the particular integral, representing the specific response to the external force. if the external force is removed, y sub p becomes 0, and the system's behavior is entirely described by y sub c. By adding them together using the principle of superposition, we capture the full reality of the system's dynamics. Before we solve an actual equation, let us outline our strategy. We will split the problem into two manageable phases. First, we will find the complementary function. We do this by setting the right side of the equation to 0, creating a homogeneous equation, and finding its roots. Second, we will find the particular integral. We do this by making an educated guess based on the shape of the driving force. For example, if the driving force is an exponential function, we guess an exponential solution with an unknown constant. This is formally known as the method of undetermined coefficients. Finally, we add the two results together. Let us put our strategy into practice with a basic non-homogeneous equation. We are given a differential equation with an exponential driving force, e to the power of 3x on the right side. First, we set the right side to 0 and write the auxiliary equation, m squared minus 3m plus 2 equals 0. Factoring this gives roots of 1 and 2, leading to our complementary function. Next, we guess the particular integral has the form a times e to the power of 3x. We substitute this guess and its derivatives back into the original equation. Simplifying the terms allows us to solve for a, which equals 1/2. Finally, we add them together for our complete solution. Now that we have solved a purely mathematical example, let us apply this to a real physical scenario. Imagine a mass attached to a spring, resting on a frictionless table. This mass is being pushed by a constant, steady wind. We want to find the general solution to understand how the mass moves under the influence of both the spring and the wind. Our approach remains exactly the same. We will first find the complementary function to understand how the mass would oscillate if there were no wind. Then, we will find the particular integral to see how the constant wind affects the mass. Adding them together will give us the true motion. Here is the differential equation governing our driven harmonic oscillator. The second derivative of x with respect to t represents the acceleration of the mass. The term 4x represents the restoring force of the spring pulling the mass back to the center. On the right side, the number 12 represents the constant, steady wind pushing against the mass. Because this driving force is a constant number rather than 0, the equation is non-homogeneous. If the wind blew harder, this number would increase, which would directly change our particular integral. If the wind stopped, the right side would be 0, leaving us with a simple, unforced bouncing spring. Let us solve the equation for our driven oscillator. First, we ignore the wind by setting the right side to 0. The auxiliary equation is m squared plus 4 equals 0, which gives purely imaginary roots of positive and negative 2i. Imaginary roots mean the complementary function is made of sine and cosine waves, representing the natural oscillation of the spring. Next, we find the particular integral. Since the wind is a constant force of 12, we guess a constant solution, a. Substituting a into the equation, the derivatives vanish, leaving 4a equals 12, so a equals 3. Adding them together, we see the mass still oscillates naturally, but the wind has shifted its equilibrium position by 3 units. To truly grasp what we just calculated, let us look at this graph, visualizing the solution over time. The horizontal axis is time, and the vertical axis is the position of the system. Notice the dashed blue line. This is the complementary function, or the transient response. It oscillates wildly at first, but eventually decays toward zero. Now look at the dashed red line. This is the particular integral, representing the steady state response forced by the outside environment. Finally, the solid purple line is our general solution, the sum of both. It starts off following the chaotic natural bounce, but as time passes, it perfectly aligns with the steady red line. We have covered a lot of ground today, so let us summarize our key takeaways. Whenever you face a differential equation with an external driving term, remember that the solution is always a team effort. The complementary integral handles the system's internal, natural habits, acting as if the outside world does not exist. The particular integral handles the system's forced response, acting as the specific footprint of the external force. By finding them separately and adding them together, you capture the complete, beautiful reality of how physical systems move, react, and eventually settle into their environments. Great job following along.